Okay, so in this lecture we're going to talk about power series. We've already seen series, so we know what it means for a series to converge, we know what it means for series to diverge, and we have our various tests that we've been using, like the alternating series test, the divergence test, the ratio test, and the root test. Okay, so what is the difference with what's a power series? So a power series, sum n equals 0 to infinity cn x to the n, or sum n equals 0 to infinity cn x minus a to the n, is a function. And here the cn's are constants called the coefficients of the series, so cn might be 1 over n. X is a variable and a is a fixed number, and this is called the center of the power series. So if I had cn x minus pi to the n, that would be a power series we would say centered at pi. So the cn x to the n is a power series centered at 0, because x is equal to x minus 0. Okay, but what is a function? So a function is a machine. It takes in x and it spits out f of x. So a power series takes in x and it spits out cn x to the n. So you hand this power series an x and it gives you a series. Okay. Similarly, for one centered at a, we hand it x and we get the sum from n equals 0 to infinity cn x minus a to the n. So let's look at an example, because this is a bit abstract. So sum n equals 0 to infinity x to the n over n factorial. And let's feed this 2. So 2 goes into this machine, and out comes sum n equals 0 to infinity 2 to the n over n factorial. Okay? So, remark, as with any function, you can only feed it certain things. If you had a machine whose job it was to assemble watches, you shouldn't feed it the parts of a car. So, with these power series machines, there are only certain x's that we are allowed to feed them. But, from this remark, we can always feed it a if it's centered at a. Now, why is that? So if we look at sum cn a minus a to the n, this is, well, if we just expand it out, write out the terms in the dot 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 notation, we get c0 a minus a to the 0 plus c1 a minus a to the 1, and so on, which is equal to c0 0 to the 0 plus c1 0 to the 1 plus, and so on. And then 0 to any power is going to be 0 except for 0 to 0. 0 to 0 is 1. So the only term that survives is c0. But in particular, this power series, whenever you feed it a, you always just get the first term c0. So a power series centered at a can always eat a. Example, sum n equals 0 to infinity x to the n cannot eat 1. If we feed this thing 1, what happens? Well, it spits out 1 to the n, but 1 to the n is always 1. So we get 1 plus 1 plus 1, and so on. And this does not converge. It'll diverge to positive infinity. So, for a power series centered at a could be 1, it could be pi, it could be e, it could be your favorite number. We'll find that it can either eat anything, so it can eat any x it wants, which we represent by just shading in the entire real line. It might only be able to eat one thing, which is just a. We know it can always eat a, and a might be the only thing that it can eat. So I've shaded in red everywhere else. Or it might be able to eat an interval. So it might be able to eat just a neighborhood of a that is this capital R wide. So it might be able to eat everything between a minus r and a plus r. Now this is a very important remark. The interval may or may not include the endpoints. So your machine, your power series, may be able to eat a minus r, or it may not. It may be able to eat a plus r, or it may not. So your interval can either be open or half closed, including the right endpoint, or half closed, including the left, or it might be able to eat both of them. It might be the closed interval. Okay. So some important terms. We have the radius of convergence. This is the width of this R, this capital R. And if we look at part 2 and 1, in part 1, R is infinity. So you can eat all of the real line. And in option 2, R is 0. Okay. Then we have the interval of convergence. And the interval of convergence is every single x that you can eat. So in 1, it's just minus infinity to plus infinity. In 2, it's just a, the 1 point set a. And in 3, it might be closed on one side. It's the interval from minus a to r, minus a minus r to a plus r, and it may or may not include the endpoints. Okay, so you have this radius of convergence and interval of convergence. So, really important, how are we actually going to find this radius of convergence or this interval of convergence? Well, we're going to use the ratio test. So, if we have our series here, I've just got a power series centered at 0, Cn x to the n. Our terms an are Cn x to the n. So, if we apply the ratio test to this, we have the limit as n goes to infinity of the absolute value of an plus 1 over an is equal to the limit as n goes to infinity, Cn plus 1, x to the n plus 1 over Cn x to the n. Now, this x to the n will always cancel with the x to the n up top, and you're just left with 1x. And then you have this limit Cn plus 1 over Cn. And if you have that this thing is less than 1, the ratio test will guarantee convergence. Okay? But remember that if the ratio test, if this limit gives you 1, the ratio test is inconclusive. So you have to check these values individually. Okay, so let's look at an example. So this is the example 2x to the n over 3 to the n over or times n squared. So let's dive into the ratio test. Lim n to infinity an plus 1 over an equals the limit as n goes to infinity of 2x to the n plus 1 divided by 3 to the n plus 1 times n plus 1 squared multiplied by, so you would divide by n, but we're just going to multiply by the reciprocal of an. And now we have all these cancellations. So our x to the n is going to get rid of n of the powers on the top. The 2's are going to get rid of each other. The 3 to the n is going to kill the 3 to the n in the denominator. And we are just left with lim n goes to infinity of n plus 1 squared divided into n squared times x over 3. Now, this n squared over n plus 1 squared goes to 1, because the power on the top is the same as the power on the bottom. So this limit is equal to just x over 3 in absolute value. Now, we want that this is less than 1. We want less than 1 to guarantee convergence by the ratio test. Okay, so we want to see for what x is this x over 3 in absolute value less than 1. So this is the same if we multiply both sides by 3 as absolute value of x less than 3. So this means that it's going to work. If we draw the number line, we are centered at 0 all the way to 3 and all the way back to minus 3. And now I haven't checked the endpoints, but I know that inside this open interval at least, we have convergence. Okay, and outside we have divergence, because remember the ratio test will give you divergence if the value is greater than 1. So we still have this r equals to 3, and we still have to check the 2 endpoints if we want to find the interval of convergence, but the question only asks us for the radius of convergence. Okay, so let's look at another example. we have the sum from n equals 1 to infinity, minus 1 to the n minus 1 over x minus 2 to the n over root n. So let's just dive straight into the ratio test again. So we have minus 1 to the n plus 1 minus 1 times x minus 2 to the n plus 1 divided by the square root of n plus 1 times, again we're going to multiply by the reciprocal of an. So in the denominator we have minus 1 to the n minus 1, x minus 2 to the n, and this is being divided into square root n. So we have to do our cancellations. Lim n goes to infinity, and the minus 1s won't matter because we're in an absolute value. So when we divide the denominator into the numerator, we're left with just minus 1, but it drops out because of the absolute value. So we just have square root of n divided by square root of n plus 1 times x minus 2. And now again, this square root n over square root n plus 1 goes to 1. So this limit goes to x minus 2 in absolute value, and we want this is less than 1. So what does this interval look like? This interval is centered at 2 now, and it goes all the way to 3 and back to 1. Now, to find the interval of convergence, we have to check these endpoints. So let's check x equals 1. Let's feed this machine x equals 1. So we have minus 1 to the n minus 1, open bracket 1 minus 2 to the n, divided by square root n. So this is equal to minus 1 to the 2n minus 1, square root n. Now 2n minus 1 is always odd, so this is just going to equal minus square root, or minus the sum, sorry, of n equals 1 to infinity of 1 over square root n. And this diverges by the p-test. This is diverges p equals 1/2. Now let's check the other endpoint, x equals 3. So minus 1 to the n minus 1, 3 minus 2 to the n, all over square root n, equals sum. Well, the 3 minus 2 to the n is just going to disappear because it's 1. So we end up with this alternating series, and we know that this converges by the alternating series test, because the bn's are 1 over root n, which are decreasing and they go to 0. So if you're confused about that last step, just go back and make sure that you understand the alternating series test, how to apply it. Okay? So overall, we have that the interval of convergence is, we don't have 1, but we do have 3. So it's this half open interval from 1 to 3. So we shade this in. So everything between 1 and 3, we don't have anything outside, so beyond the endpoints. We don't have 1, so I'll indicate that with a red dot, and we do have 3. I'll indicate that with a green dot. Okay, so that's that example. Now let's move on to representing functions as power series. So recap from what we've just done, we wrote down the power series centered at a, and we saw that these are functions of x. We saw that we used the ratio test and on them to find the radius of convergence, and to find the interval of convergence we have that interval plus maybe the endpoints. So you check the endpoints individually. So now what we're going to talk about is, can we take functions that we're used to dealing with and express them as power series? So again, what we've done is we've thought about power series as functions, okay? But do they coincide with functions that we already know? As in, can I take a function that I know, that I've dealt with before in different parts of my calculus career, and can I represent it as a power series? So another question then is, if I can do this, where is it valid? And now hopefully this example will motivate what I mean by these questions. So, key example. Consider the function that's defined on the entire real line except at 1. F of x is equal to 1 over 1 minus x. Okay. So, recall the geometric series formula. For absolute value of r less than 1, this sum from n equals 0 to infinity, r to the n, is equal to 1 over 1 minus r. Okay. So, r is just a letter. Let's replace r with x. So, for absolute value of x less than 1, f of x, which is 1 over 1 minus x, is equal to this sum. Okay? And I have a star here because this is very, very important. We're going to use this a lot. So we've taken this function f of x, that was a perfectly reasonable function that you've all seen before in different parts of calculus, and now I've written it as a power series, and this representation is valid for absolute value of x less than 1. So let's look at an example. Can I use this thing, this starred box that I have, to write other functions as power series? So, g of x is 1 over 1 plus x cubed. Now, I want to think about how can I manipulate this star, this box. So, x again is just a letter, r is just a letter. I could feasibly write 1 over 1 minus y, or 1 over 1 minus chair, is equal to sum n equals 0 to infinity chair to the n, and all I would need is that the absolute value of chair is less than 1. So, if I can represent g as 1 over 1 minus something, which I can do by writing g is 1 over 1 minus x cubed. Sorry about that. And now, I look at this and I think, well, I can plug into this formula. Instead of x, I'm using minus x cubed. So, I have minus x cubed to the n, from n equals 0 to infinity. And then I multiply this out, and I'll get sum. So again, I'm using this x cubed is this sort of thing that I'm plugging into the thing in the blue box. And this is equal to minus 1 to the n times x to the 3n, from n equals 0 to infinity. So I've taken this function g that I didn't have a power series representation for before, and I've written it as a power series. Now where is this valid? So this would be valid for when, to use this step here, I need to have that whatever I'm using this formula on has absolute value less than 1. So here I need minus x cubed has absolute value less than 1. But that is the same algebraically, if you can prove it, is just the same as the absolute value of x is less than 1. Okay, so I have this power series representation for g of x, and I know where it's valid. So now we move on to differentiation and integration of power series. So power series are functions. Are they differentiable functions? Are they integrable functions? So this theorem says that if I have Cn x minus a to the n, and it converges on centered at a radius r, okay, so it's a perfectly defined function on an interval around a of radius r, then if I think of it as a function, it is differentiable and therefore continuous on this interval, and the derivative is this, n equals 1 to infinity n Cn x minus a to the n minus 1. So, what is this? This is pretty much that if you have a power series that converges on an interval and you want to differentiate it, you can differentiate it term by term. And then the second part says that if you want to integrate it, you can integrate it term by term, and you pick up this constant of integration. Okay? So again, if you want to differentiate power series, or you want to integrate power series, you do it term by term. Now, why is this useful? Let's say you have a power series representation for a given function, and you want to find the power series representation for its derivative. Well, this tells you take the power series representation you have for the function and just differentiate it. It's term by term. So, we'll look at an example. We have h of x is equal to 1 over 1 minus x squared. So, 1 over 1 minus x squared is d dx of 1 over 1 minus x. So it's the derivative of 1 over 1 minus x. And now if I apply the rule, I can represent 1 over 1 minus x for absolute value of x less than 1 as d dx of the sum from n equals 0 to infinity x to the n. Okay, and now if I just expand this out as d dx of 1 plus x squared plus x cubed plus so on, I can differentiate this term by term. If I differentiate 1, I get 0. I differentiate x, I get 1. Differentiate x squared, 2x. Differentiate x cubed, I get 3x squared. And then, if I just write that as a power series, this is the sum from n equals 1 to infinity n x to the n minus 1. Now notice my new power series starts at 1. That's because whenever you differentiate, you're going to kill the 0 term because it's a constant. Okay? So just if you go back and look at that formula I have for the derivative of the power series, that is going to start at 1 because you kill the constant term by differentiating it. Okay, so now I have this h of x function that I didn't have a power series representation for before, but now I do, just differentiating a function that I did have a power series representation for. So we're using what we have to get more stuff, which is pretty much how you do any kind of mathematics. Another useful thing is that a lot of you had questions, or there were questions from class or from homeworks of, like, you have all these tests to show that series converge, but what do they converge to? So representing functions as power series is a great way to actually find out what that is. Okay? Like, find out what does this mad series actually equal. Okay, it allows us to have some very interesting equalities. So, if I have this example, let's go back to just the example we just did, 1 over 1 minus x squared. This is equal to this sum n equals 1 to infinity n x to the n minus 1. Now, I have x's, I can let x be a half on one side, and that has to be the same if I let x be a half on the other side. So, let's actually plug into both sides. 1 minus a half squared divided into 1 is equal to, well, I fill in a half into this power series. So I get a half to the n minus 1. And now, if I do some algebra, 1 minus a half is a half, is equal to sum n equals 1 to infinity n times a half to the n minus 1. And then the left-hand side is clearly just equal to 4. So, I have this n over 2 to the n minus 1, sum from n equals 1 to infinity, is equal to 4. So I have this crazy looking series that I could have proved converges using other methods or whatever. But now I know what it converges to. So that's very useful. Right, so let's dive into some examples of this using differentiation and integration to find power series representations of functions. So, question 1. I have 1 over 2x minus x squared, and I want to use this blue box formula, because that's what the hint says. So, let's try and write. Remember, if you want to apply the blue box, you're going to try and write the function as 1 over 1 minus something. So let's just do that. This has to be 1 over 1 minus 2x plus x squared, divided into 1. And now we can see algebraically that 1 minus 2x plus x squared is just 1 minus x squared, as in 1 minus x all squared. So now I can write this as n equals 0 to infinity of 1 minus x all squared to the power of n. And this equals the sum from n equals 0 to infinity of 1 minus x to the 2n. And now I see that they've actually represented it as x minus 1 to the 2n. So, but because the 2n is always even, I can just change the inside, as in minus 2 squared is the same as 2 squared. So I can change the sign inside. And now back here, if you were being very careful, you should have, alarm bells should have gone off. This is only valid for 1 minus x squared less than 1. And this is the same as x minus 1 absolute value is less than 1. And that's where this expansion is valid. Okay, next example. We're going to do 2 more examples. So, penultimate example. We want a representation for this f of x is 5 over 1 minus x squared. And we're going to use that we have a representation for this g. So, the thing to notice is that this f is the derivative of this g. And now, if you don't believe me, g of x is equal to, well, 5 times 1 minus x to the minus 1. I'm going to differentiate this using chain rule. So this is 5 times minus 1, 1 minus x to the minus 2 times minus 1, and voila, we have f. So now we have f of x equals g prime x, which is d dx of 5 over 1 minus x, and now this is equal, but remember, only for absolute value of x less than 1, this is equal to d dx of the sum of n equals 0 to infinity, and I multiply in the 5, so x to the n, and I have this 5 in here. Close that, and then my theorem says that if I want to differentiate this series, I just differentiate it term by term. So what is the derivative of 5x to the n? Well, that's just the sum from n equals 1. Again, I'm starting at 1 because I killed the constant term. The first term is 5, and that dies when you differentiate it. And I just end up with 5n to the x, or times x to the n minus 1. And this is valid from 0 to 1, and all the way back to minus 1. But we may or may not have the endpoints, so you have to check those. Because the ratio it has to remember is when this is less than 1. Okay, so we have, when we fill in 1, we get the sum from n equals 1 to infinity 5n. And this diverges because you're adding 5 plus 10 plus 15 plus etc. The limit as n goes to infinity of 5n is infinity. In particular, it's not 0. So this diverges by the divergence test. So let's fill in x equals minus 1. And we're going to have minus 1 to the n minus 1 times 5n. And again, this diverges by the divergence test. Okay? Because now this is alternating, but your terms are getting larger and larger. Remember, for any series to converge, you need that the terms go to 0. These terms don't go to 0. Okay, so now we have convergence on the open intervals from minus 1 to 1. And we've shown we have divergence outside there, so to the left and right. And now at the endpoints, we've shown that we have divergence at 1 and divergence at minus 1. So in particular, the interval of convergence for this one is just open bracket minus 1 to 1. So the answer is D. Okay, last example. Show that the sum from n equals 0 to infinity minus 1 to the n x to the 2n is equal to 1 over 1 plus x squared. So I'm going to use the same parlor trick using the blue box. This is 1 over 1 minus x squared. Now for minus x squared less than 1, so for minus x squared less than 1, which is the same thing as the x in absolute value less than 1, is equal to sum n equals 0 to infinity minus x squared to the n. So over here now, I have 1 over 1 plus x squared is equal to n equals 0 to infinity of minus 1 to the n x to the 2n for absolute value of x less than 1. Okay, so I've taken this function and I found a power series representation for it on this interval. Now, if we look at part B, we have minus 1 to the n, 2n plus 1, and we look at this 2n that we have up here. We can think, right, what's the difference between this series and this series? Well, the power even that I have is 2 to the n plus 1 versus 2n. So, I can think about, how can I get this 2n to be 2n plus 1? Well, I can integrate. So, if I integrate 1 over 1 plus x squared, then I know that's just arctan x plus c. And my power series representation says that if I integrate 1 over 1 plus x squared, this is the integral of the sum, minus 1 to the n x to the 2n dx. And again, this is only valid for absolute value of x less than 1. N equals 0 to infinity is equal to the sum from n equals 0 to infinity of minus 1 to the n x to the 2n plus 1 over 2n plus 1. And remember, I'm integrating with respect to x, so I leave the n's alone, plus c. So now I've got this power series representation for arctan, okay, because I have this equality in the middle. And now I know that if I plug something into arctan, that's going to be the same as plugging something into this series. So I need to think, what do I have to plug in to my series down here to get this series in part B? And I see that I want a root 3 on the bottom. So the candidate for plugging into this is going to be x equals 1 over root 3. So let's plug in 1 over root 3 into arctan. So pi over 6 is equal to arctan 1 over root 3. But this is equal to sum n equals 0 to infinity minus 1 to the n, 1 over root 3 to the 2n plus 1. Because 1 over root 3 has absolute value less than 1, I'm allowed to plug in here. So this is equal to n equals 0 to infinity minus 1 to the n over 2n plus 1 times root 3 to the 2n plus 1. So I have this mad series here from part B actually converges to pi over 6. So that's an example of the evaluation if you ever encounter this series in the wild. Now, not only do you know that it converges, but you know it converges to pi over 6. Okay? So that's the end of this lecture.